Welcome. Thank you for having me. I'm going to talk. So I just to give you a little sense of who I am, I work on astrophysics at all levels. I got into astrophysics from the side of dark matter, cosmology and dark matter. What's the dark matter? And during my career, we also discovered that there's dark energy. And I still work on the dark matter with about half my time, but our approaches for finding the dark matter have switched to more kinematic approaches inside the Milky Way. So I still do some large-scale structure. I still work on very large projects and work on some things that connect to particle cosmology. But most of my work these days is about dynamics and kinematics applied to the Milky Way and also to other solar systems other than our own. So I work on a lot of different things. The unifying thing about my research is it all involves very difficult or challenging data analysis. So I am going to treat my statistics lectures as really being data analysis lectures, and I'm going to talk about data analysis. And I'm going to talk about data analysis in a general enough way that I think it would apply to almost any kind of thing that people here work on. Now, how many people here are accelerator-oriented? Just raise your hands. The accelerator crew at the edges. Who is like lab-oriented, like direct detection lab experiments? Nothing. One, yes, good. Theory? Good. And what about astrophysics/observations? Good, okay, good. That's quite a breadth. What else didn't I ask? Yeah, who does lattice gauge? Who knows the mass of the proton? Who can compute the mass of the proton? Okay, good. What was I going to say? Oh, yeah. Data analysis, in my view, data analysis involves a scientific question and data, obviously, but then when you ask methodologically, what else do you need? So you need statistics, which is what the title of what I was asked to talk about. But for me, there are three really methodological domains that are all connected around in data analysis. Statistics is only one of them. Another one is applied math. And many people who haven't really delved into statistics might think that statistics is kind of a branch of applied math. But that is not true. Statistics is an independent discipline from applied math and contains concepts in it that mathematics doesn't have. For instance, the concept of causality or the concept of experimental design. Those are concepts that come into statistics that are not in applied math, but obviously there's a lot of overlap with applied math. And some of the things I'm going to talk about really you might put in the context of applied math. There's another important area that overlaps as methodological, which is computer science. And I'm not going to talk much about computer science in the next 5 days unless you want me to. You're about to hear that I'm going to crowdsource my last 2 lectures. So if people want to hear about computer science-oriented topics, we can talk about that. I have published in all 3 of those areas, statistics, applied math, and computer science. My love is astronomy. I teach physics, so I'm at the border of kind of 5 fields. One more thing I wanted to say. It's completely gone. Oh yeah, the lovely thing about data analysis is data analysis sits not just at the interface of those methodological domains, but it also sits at the interface of theory and experiment. The best data analysts will understand both the theory and the hardware. And if you can't understand both, you will be missing some piece. And that's one of the reasons that large data analyses are often done by large teams. Like in the Sloan Digital Sky Survey, our pipelines are written by, of order, 50 people. A typical pipeline would be about 50 people who have different expertise in hardware and electronics and data management and so on. Yes, hit me. I was asked to define pipeline. I won't define pipeline fully, but what I mean by pipeline is the set of software that takes the raw data off of the instrument readouts and ends with numbers that get published in scientific papers. So for me, thinking about the Higgs, the pipeline would be all of the code from the raw outputs of the Atlas detectors to the number written in the abstract of the Higgs paper. And CMS too, but I know Atlas better. Right, so in fact, a lot of data analysis is about writing pipelines, and I'm not really going to talk about the engineering behind writing pipelines, unless people want to, in which case we could put some of that into the my later lectures. One other thing I wanted to say, I could just go on philosophically. This is going to be a very philosophical lecture in general, but thank you for that question, and I encourage questions. Please stop me if I'm going off the rails or saying things that are like, duh. And one more piece of philosophy. Oh yeah, I don't see any distinction between engineering and science. So I went to college to be an engineer, and I got seduced into physics because physics was so beautiful. I ended up getting my degree in physics, and I got my PhD in physics, but my true heart is in engineering. And I see physics and astronomy as great places to do very, very high-end engineering. And it's really high-end engineering in the sense that we're always innovating, we're always making new prototypes, and in fact, almost everything we run at the end of the day is a kind of cutting-edge prototype. So I think that experimental physics and observational astronomy are just great places to do very, very sort of bleeding edge engineering. And engineering for me is not a bad word. Okay, good. Shall we? Yeah, hit me. Good, philosophical question.
So in your case, you're giving a lecture on statistics to a bunch of physicists. Did you formally learn statistics, or did you do most of us?
Great question.
Exactly what you needed, exactly at the time you needed it, and that was it?
Great question. I was just asked, did I formally learn statistics, or did I learn it on the job, as it were, just in time, as it were? The answer is I learned it on the job just in time. I have literally never taken a course in statistics. And I've also never taught a course in statistics. For those watching at home, the question is there a better way? Yes, there is a better way. Well, let me say a few things. First of all, I'm working on that. So probably people here haven't heard of it, but we run a set of meetings called Astro Hack Week. And there's a set of related meetings called Neuro Hack Week and Geo Hack Week, which were born out of Astro Hack Week. Astro Hack Week is something we've been doing as a way to kind of think about what is the curriculum, what is the engineering, statistics, computer science curriculum for astronomers. And I'm also at the Center for Data Science at NYU. That's also a place where we're thinking a lot about how do we make sure that domain scientists like physicists are also very good data scientists and are doing responsible things with the data. Those questions are currently unanswered. One of the reasons is that most things that or the overlap integral between what a physicist needs from the statistics community and what the statistics community teaches in a typical statistics sequence is not the right overlap integral. That's one thing to say. And then another thing to say is nobody wants to put aside any fundamental physics content for statistics and data analysis content, which of course is a mistake. The physics community is making a mistake insisting that everybody learn Hamiltonian dynamics and nobody learn how you properly invert a matrix so that you're numerically stable. But I have to say, the way I learned this material is through friendships. I ended up becoming a statistics expert within the astrophysics community by becoming friends with certain mathematicians, statisticians, and computer scientists who showed me that I could do my work a better way. And I think that right now, you guys are at the cusp. The generation younger than you will get some better data analysis training than I did, but you're at the cusp, so you won't. And that means that you should walk across the quad to the other departments. And your three relevant departments are statistics, applied math, and computer science. And I predict that you will find people in those departments who actually want to help. I have certainly had no trouble with that, which is interesting because I would have thought, oh, our problems are so boring, no statistician could possibly care. But that turns out not to be true. Most statisticians, applied mathematicians, and computer scientists want to show that their research does real things. We discovered a bunch of planets using some methods from causal inference. And then my statistics colleagues are like, we found planets around other stars, check this out. They loved that. We gave them opportunities to do important things. And they gave us tools that we wouldn't have found otherwise. So I did learn it just in time on the job. I think that is the wrong solution, but I think there's going to be an element of truth to that, whatever we do. In some sense, a lot of the knowledge that physicists have is implicit knowledge. It's the knowledge you learn from your advisor. My students are like me in certain ways, and students who weren't my students are different from me in certain ways because so much of our knowledge is implicit knowledge. And right now, everything I'm going to tell you is implicit knowledge. It's not stuff you learn in the curriculum, but we are trying to build a new curriculum. That is a goal of the Center for Data Science at NYU. There's several other centers for data science that are growing around the country that are trying to do that, and it is the goal of these Hack Week projects we've been doing. So look for Physics Hack Week. I hope that happens soon. And Astro Hack Week, Geo Hack Week, and Neuro Hack Week are open to all, including even physicists. Okay, good. By the way, who here is not a PhD student? Okay, good. And who here has not taken general relativity? Two people have not taken general relativity in this whole room. You haven't taken it, but you've taught it? That's like me in statistics. Okay, good. The only reason I asked that, it's interesting that people have taken general relativity, because you're going to see later on in this week that statistics and general relativity have a huge amount in common, which is very odd. But it's because many operations in statistics are fundamentally geometric operations. And general relativity is the only really sophisticated interaction any of you have had with geometry. And so so I finally understood general relativity after doing statistics. So we'll see that. That'll come up over the week. I like to emphasize that to physicists because it's another intellectual hook, another reason that even if you're a theorist, you should pay attention. Okay, good. I'm going to write a set of principles down on the board. All I'm going to try and do in this 75 minutes, I have 57 of them left, I'm going to try to write a set of principles down on the board, which should guide any data analysis you ever do, and is also a set of questions you can ask of people when you're suspicious of their data analysis. And then in the next 4 lectures, we'll try to do things that illuminate these principles. So try to keep a little track. I also wrote the principles in the wiki on my lectures so that I would remember them and make sure that I come back to them. And you can also ask whether I'm connecting to those principles as we go. Okay. The first principle is that methods flow from assumptions. So whenever we do a data analysis, or whenever you're doing some data analysis, say you're trying to measure the mass of the Higgs, you do some operations on the data. The operations you do on the data should be the natural operations which emerge from your assumptions about the data. And these assumptions will be there'll be assumptions about how the data were generated. Sorry, I won't be grammatical on the board. How the data were generated, and for some of you that might be triggering the word likelihood function. There's something about a likelihood function. We're going to come back to that. That will be the whole subject of the next lecture, more or less, the likelihood function. So you're going to make assumptions about how the data are generated. You're going to make assumptions about the physical model. Or you could even call it the theory model, meaning that it's the standard model plus the standard model Higgs, but you don't know the mass. You have some free parameters but that you don't know, but there's a whole structure that you do know. You're going to make a set of assumptions like that. And then there's going to be assumptions about what I'll call the hardware. But this could be like, you know, how the calorimeters work and how data gets censored and how they bunches get overlapping and stuff like that. So there's going to be assumptions about the theory model, your hardware, and then some additional assumptions. Yes?
What's the difference between 1 and 3? Because how your data is generated seems intrinsically related to.
Yeah, so the question is, what's the difference between how your data is generated and your hardware? They overlap heavily. These distinctions, I'm not really trying to make a mutually exclusive, exhaustive list. I'm more saying things you need to think about. There are certainly aspects about your hardware, though, that don't come in here very obvious. There are things about censorship in your hardware that mean that you don't get certain kinds of data, but it isn't exactly how your actual data were generated. So that's why I feel like there's a little bit of distinction there. But you could put these two together if you wanted. And this is what I said, you know, when I said the best data analyses, you have to understand both the theory and the hardware. And that's what I love as both a physicist and an engineer. I'm at the best place, the place I want to be. Now, sometimes you want to use a certain method. Sometimes there's a method you want to use. You're like in undergrad lab class and you've like measured some positions of a ball as a function of time and you do a least square fit to a log-log plot or something. And you want to, like you're just told in the lab manual, do a least square fit. If you choose a method, you get the assumptions that come with it. See what I'm saying? This could go either way. You're allowed to just choose a method and use it, but then you are adopting a set of assumptions. Or you can write down assumptions and that will deliver to you your method. But you can't separately make these decisions. People see what I'm getting at? Okay, I'm going to illustrate that really, really specifically next lecture. We're going to write down a set of assumptions, which will lead us to do a very simple data analysis. And then we're going to look at how brittle the situation is, meaning if we make any small changes to the assumptions, it totally screws our data analysis. Yes?
What do you do if you're not sure what your assumptions should be? Like if there's something in your model that
Good. Great question. Question is, what do you do if you don't know what your assumptions should be? So I would say a few things. One thing I would say, so you never know, by the way, I'm going to come back to this in maybe the next point. You never really know that your assumptions are true, and you never really know, you're always floating in this world, like the physical model in my head lives in some latent space you can't see. All you get to see are these data you get. You can see your hardware, see your data, but you don't get to see this model, so you don't actually know whether it's true. But in order to do any operation on the data, you must make assumptions. So my position is you don't know your assumptions are true, you're just making them. You have to make them. Now, it's better to make ones that are more true. But you'll always be in a state that you don't know which assumptions are true and which are false. And of course, the assumptions, when I say you're making assumptions, it doesn't mean that these live in some magical fairyland. We can test the assumptions. We can go back and look at whether the assumptions look like they're, like you might assume your data are normally distributed around some mean. Well, you can go and make a histogram and check whether it looks normally distributed. So it's a testable, these assumptions tend to be testable, but they must be made in order to do an operation. You can't do an operation without making assumptions. And some people feel like they can. They feel like, oh, well, we just took an average of the data, and so we made no assumptions about the physical model. We just took an average of the data. But even taking an average of the data involves certain kind of assumptions about stationarity, about error noise distributions, and so on. It's only a legitimate thing to do under certain circumstances. So now, but another answer to your question is, sometimes you choose the method you want to do, and then you let the assumptions flow from it. So sometimes you just say, we're doing this method, therefore we are implicitly assuming the following things. But the only honest thing you can write in your paper is, because we use this method, we implicitly made these assumptions. It's dishonest to speak otherwise. Which relates to the second point I want to write down. Which is, Let's even number them. All data analysis is technically subjective. And we physicists don't always like this. We physicists tend to think that we have a direct window onto the world, and we see the Higgs boson and its mass, and we see that all is good. But we do not have any kind of objective view of the world at all. So for instance, you could imagine one way you could show that the Higgs mass really is 125 GeV is you could construct every possible physical law and test every possible physical law against all the CMS Atlas data and all other data that have ever been produced in the history of physics. You could do that. That would take much more than a countably infinite length. Well, it might only be countably infinite, actually, because like famously Gödel ordered all computer programs. And I think if you write down a certain set of operators, you could probably order all possible physical theories and then do some kind of infinite integral in all parameter spaces of all those theories or something. So it might only take a countable infinity to do that. But there's no sense in which we've done that. We have chosen to test very particular theories in very particular ways. And we've chosen to make certain assumptions about the data and certain cuts and certain times when we thought the instrument could run and certain times we couldn't, and so on. There are an enormous number of decisions that come into every data analysis. And why did I say technically subjective? What I mean is not that you just like do whatever you like. It's like making a painting. I mean, it's subjective in the sense that your choices depend on your knowledge and your beliefs. They depend on your experiences, your knowledge, your beliefs. You will make the choices that are consistent with your choices, your knowledge, and your belief. That means you will make other different decisions from other scientists. In your data analysis, you will make different decisions from others because they have had different knowledge, experiences, and beliefs. And they might be just as rational as you are, but if two people have had different experiences, they will have come to different conclusions, and they will have to make different choices for their data analysis.
But
Yes?
surely there is a common set of experiences that everybody believes in because of historical
Good.
testing of the laws of physics over hundreds of years.
Yes, there are certainly a set of shared principles that we all in this room agree with. That's absolutely true. For instance, most people in the room believe that the fundamental laws of physics are managed by general covariance. And most of us believe that at microscopic scales, quantum mechanics holds sway. But the assumptions that we hold in common, that all of us hold in common, are not a sufficient set of assumptions in order to do a data analysis. There are always additional assumptions you have to add, and those assumptions come down to very detailed properties of outliers, possible extensions to physical law, possible places where there might be confusing backgrounds or flexibilities for backgrounds, all sorts of things that are not covered by our shared beliefs, but are required to be specified in a data analysis. Good. But even if everyone agreed, this would still be true. Even if everyone agreed on all details ever, it would still be true. It's still technically subjective, because if the physics community had a different set of experiences, it would be doing something different here. Okay, good. That is technically undeniable. Now, whether it's important is a matter of debate, and that's kind of what came up just there. Okay, good. Do I still have a movable board? Yes, I do. Okay, good. 3. Don't make things up. What do I mean by that? Often you have some complex piece of data and you can see it's got some outliers and there's some slope there, and so you say, well, these points are probably outliers, and then I'm going to take a median of these, and then I'm going to take a median of these, and I'm going to look at the difference in those two medians as a function of where I put the cutoffs, and then I'm going to make a plot of that, and then that's going to be my result. That's what I'm saying don't do. There's two aspects to not making things up. The first thing is just a repeat of point one. You should write down assumptions and a method that connects to those assumptions, or write down a method and see what assumptions it's based on. But you should be doing something where you have method and assumptions connected. That's the first thing. And the second thing is there's a huge, huge literature. And that literature even includes things like proofs. Like, for instance, linear regression is proven to be unbiased when the assumptions of the regression are true. So, like, if you make data under the assumptions and then you do linear regression, you get unbiased answers, and there's proofs. And in fact, the proofs have quite a bit of generality. For instance, another thing is jackknife or bootstrap. These methods, they're these empirical methods of getting error bars, jackknife and bootstrap. There are huge literatures about those methods, and there are proofs for when they're valid. And there's a huge literature on how you should cut your data and what folds you should do and so on. Don't just make things up. Try to make some attempt to understand what's known, what's proven, what's valuable, and what the statistics, applied math, and computer science communities have got solid results on. And this is a problem I am battling in astronomy all the time. But good examples of where people did not just make things up are the joint analysis of the Higgs. That was a beautiful set of papers where obviously you can quibble with details because the details are subjective, but fundamentally the methods that were used were very solid methods, very well substantiated by the statistics teams, and the joint analysis is undeniably excellent. Another place that's incredible is the LIGO events. If you look at the data analysis underlying the LIGO events, it's beautiful. Every stage they did in the data analysis, they used trusted, understood methods that are understood in multiple communities. So it's always tempting to make things up because things go wrong. Things don't meet your assumptions, but it's better to do an analysis that has slightly wrong assumptions than an analysis where you don't know at all what you're standing on. Because when you make wrong assumptions, you at least have a method that you know is right there's some limit in which it's correct. Whereas if you make things up, there'll be no limit in which what you've done is correct, which is worse than the average data analysis. Worse than the median anyway. Okay. Next, linear algebra. What are we on, 4? Linear algebra is your best tool. Actually, let me write it as most important. It's your most important tool. I have learned so much linear algebra in the last 10 years, and not a single thing that I use in linear algebra existed at all in the undergrad linear algebra course I took in college. Not a single thing. My linear algebra class in college, for instance, never had a non-square matrix. Okay, already that drops almost everything I've ever done. And then it never dealt with how you numerically manage a matrix. Like we learned some algorithm for row reduction or whatever, which you would never use ever in a calculation with the matrix. And we never did anything with structured matrices, never did anything with sparse matrices, nothing. All the things that we know that are so important to data analysis, not a single one of those things appeared at all in any form in the undergraduate linear algebra course I took. Useless. But some of those things do appear in general relativity. And that's why there's a connection to general relativity, because of course linear algebra is the language of geometry. And I'm going to really try to highlight that in the next lecture. We're going to write down the likelihood function for some data, and you're going to see inside the likelihood function there's going to be a metric distance between the data and the theory. And that metric distance will have a low-rank metric in there, which would be like some crazy space in general relativity, some singular space. So I cannot recommend this highly enough. The more linear algebra you know, the more powerful you are. And a lot of the work that my group does is making linear algebra faster and more accurate. Yes?
As someone who's never taken a linear algebra course in my entire life, can you recommend a good book as far as
Oh, that's a great, the question is there a good book for linear algebra? The famous book for linear algebra is by Strang, S-T-R-A-N-G, and it's called something like Linear Algebra. But it's not that useful for data analysis, I think. In fact, I've never really seen the right thing for data analysis. There's a very good book, which I will probably mention again later in the week, by Bishop, called Pattern Recognition and Machine Learning, or Machine Learning and Pattern Recognition. Do people know that book? Who here has looked at that book? Good, that's a great book. That book does a lot of useful math. And it's really aimed at people who are trying to learn machine learning, but a lot of the math in there is very useful for physics. There's a very good book by David Mackay, who's a physicist, M-A-C-K-A-Y, called Information Theory, Inference, and Learning Algorithms. That book is a masterpiece, but it is much more focused on the probability than the linear algebra. But if you read between the lines, there's a lot of linear algebra in there. David Mackay died this year, unfortunately. Okay, good. What else was I going to say about? Oh yeah, I had to mention, I wanted to write down on the don't make things up. I forgot something here. I wanted to write that I said huge literature, but another thing that I mentioned earlier is you have colleagues. And when you find yourself making things up, that's a great opportunity to go over to the stats department or the applied math department and say, I feel like I'm making shit up here. Because they can often point you to methods that solve your problem that aren't made up. Linear algebra, where are we? Okay, good. Various things in linear algebra that, as I was saying, I didn't learn in my undergrad linear algebra course. One is that matrices are always ill-conditioned. Basically, all matrices you ever produce in data analysis are ill-conditioned. What does ill-conditioned mean? It means that the largest eigenvalue of the matrix is far larger than the smallest eigenvalue of the matrix. So if you find an inverse, it's actually just zeroing out large parts of large parts of it don't matter. You know, if there's 45 orders of magnitude between your largest eigenvalue and your smallest, which is not uncommon at all in data analysis, there's no way that this eigenvalue can enter into any linear algebra that any normal computer does, because if you add 10 to the minus 45 to 1, you get 1. This is a big thing that we think about a lot in our business. Another thing is that linear algebra, if you look under the hood of what your linear algebra system on your computer is doing, it's actually doing optimizations. The weird stories you learn about how you invert a matrix or whatever in high school don't have anything to do with how matrix operations are written on computers. Matrix operations written on computers are like optimizations. And as you learn about these optimizations, you find you could open the hood, and then you can use those optimizations for other things, or use them more directly. So there's a lot of interesting material in here. And the more you learn here, the stronger you'll be. And the nice thing is, this also helps your theory side as well, because linear algebra is also incredibly important to theory. Like for instance, I only finally understood what a Hermitian matrix really is by doing data analysis. There's a moment in data analysis where your matrices become Hermitian, and then you realize you're on the right track. Because basically everything in physics is Hermitian, including the operators that used in data analysis. Okay, good. Good. Next. 5. In the end, I'm going to call it data analysis. Data analysis is used to, why are we doing data analysis? Why are we doing data analysis? We are doing data analysis to make decisions. Now that sounds a little strange. You might think you were doing your data analysis to find out the mass of the Higgs boson, but you were not. You were doing that data analysis to figure out what you would write in the abstract of the Higgs mass paper. And that might sound like a funny distinction, but it's a real distinction. You're not doing data analysis so that you are better off. You're doing data analysis to provide something back to the community, which might be a paper. It might be some result. It might be some posterior probability over something. It might be some intermediate data product that somebody else can use. But those things are the results of your decision making, and your decision making is based on your data analysis. Or another example is when the Higgs is found, it's measured. Now the question comes up, is it the only Higgs, or are there multiple Higgses? So now you do more data analysis, and you have to decide whether to continue to pursue this idea that there's multiple Higgses or give up. And that's a really big decision for you at your stage, because you can easily go off and work on something that nobody cares about. And whether or not people care about it is a combination of whether it's likely to be true and whether it's likely to be true and whether it's going to be important somehow. It's like some combination of truth and importance that makes something valuable to go on. And I'm going to come back to that in just a second. What's data analysis doing? It's bringing in the information about like truth or about the support for this model. Like, does this model do a good job of explaining the data? Obviously, working on multiple Higgses is a bad idea if nobody cares, but I think people do care about that. But then it's even more important to work on it if the data suggests that maybe there is a second Higgs. If a second Higgs starts to appear, you will decide to do different things with your life. So you really are using the data analysis to make decisions. But I think a very focused decision to think about is you actually have to put a number in the abstract of the paper. That's what I really like that decision, because it's a really important decision. It's absolutely critical to your future what number you write there, and you are making that decision on the basis of a data analysis. Now I'm going to tell you something horrifying. The data analysis alone does not tell you what number to write in the abstract. And if anybody here has done a significant data analysis, they know this, because they've made a whole bunch of assumptions, and you like tweak the assumptions, and this assumption's a little weird, but it fits the data better, and it gives you a slightly different Higgs, and then you do something else, you get a slightly different Higgs, and you get like 10 different numbers, all with different probabilities over the data, and all sorts of other beliefs you then have to believe about the calorimeter. Like, if I believe that this Higgs is right, then maybe there must be a flaw in the calorimeter, because otherwise we would have seen events like this. It's always a mess. At the end of the day, you have lots of different answers that are conditioned on slightly different assumptions, and you have to decide what number you're going to put in the abstract. You are not allowed, in the current literature, you're not allowed to write a probability distribution over abstracts. Although we have been thinking about that, because it is actually kind of interesting if you could produce a probabilistic publication. The crazy thing about this is this requires more than just data analysis. This requires utility. Meaning you have to make additional subjective assumptions. In addition to the assumptions you made in making your data analysis, you also have to decide, is it worth mentioning in the paper that when we made this other change, we got a slightly different answer? Is it worth mentioning that? And that question involves a data analysis aspect. For instance, if it made the fit to the data much better, you'd be like, yes, I think we should mention it. And also a utility, because it might be that you have to invoke ghosts or God or something to make it work, in which case you think, well, that might be bad for my career. And I'm not saying that this is bad. I'm saying that this is unavoidable. It's technically unavoidable. Nothing in frequentist statistics nor Bayesian statistics tells you how to make a decision. All they do is give you probabilities over certain kinds of things. Frequentism gives you probabilities over data. Bayesianism gives you probabilities over parameters. Nobody tells you what number to write in the abstract. In order to write something in the abstract, you have to do some integral over utilities or over outcomes. And now, of course, you don't actually do that. You just say, let's just use the median of the sampling or whatever. But you have applied your utility when you made that choice. And again, I mean, technically. It's not literally that we all sit around and talk about our utility all the time. It's that technically you cannot write something in the abstract without having exercised your utility. So it is technically additionally subjective. Yes?
To what extent does the utility overlap with the making things up?
The question is, in what way does the fact that there's a utility relate to making things up? It does relate very strongly. That is an insightful question. At some level, we often do extremely principled data analyses, and we've done some very beautiful MCMC sampling, and we've shown that it's convergent with all sorts of different starting points, and we've tried different models, and just this gorgeous set of things. And then in the abstract of the paper, we go, there's no real evidence for dark matter in this experiment, or whatever. And then the question is, didn't we just make that up? Because isn't that just a statement of our utility rather? So yes, right. What I'm saying here is don't make things up when you have alternatives. But at some level, you will have to make some kind of hard cuts at the end of the day. At the very end of the day, you're going to have to make some hard cuts to decide what you write in that abstract. And it's very nice to see, by the way, sometimes when people hear me talking about subjectivity and utility, they think, oh, it's just my choice. But that isn't true. Think about the Higgs mass. The Higgs mass paper was written by an enormous group of people. In fact, you've probably, who here is on that author list? I was in one of the PhD defenses was actually on the number that was in the combination paper, and the author list is far, far larger than the paper. So when I say subjective, I mean it involves things that include the knowledge and beliefs of that community. Not necessarily knowledge and beliefs and utility of an individual. It's the knowledge and beliefs and utility of the community that wrote the paper. And one of the reasons that these big particle physics collaborations produce very reliable, very conservative answers is because they do have to come to a consensus about their experience and their utility, and that's a very good thing. I think there's also room for the mode we work in astrophysics where everyone writes their own papers and they're all allowed to do all their crazy stuff. But there's much more divergence in the astrophysics community about what is concluded from a particular piece of data, because as the author lists get shorter, there's less consensus between teams or across papers about what's true and what's undeniable and what's likely and what's important and so on. It's an interesting thing that also connects to academic freedom in a certain way. Okay, good. I'm just making the point that it's technically unavoidable that your utility comes in. That's all I'm saying. And so I'm sort of kind of preparing people to object when somebody says, well, we've done this, there's no better analysis that's possible, we've finished this problem, we're done. That's never true. And by the way, one of the big problems for particle physics, a huge problem for particle, you mentioned open science when you introduced me. One of the problems for particle physics is, of course, our knowledge changes over time. So you finish running all the LEP data or whatever, and do all your experiments, you get all your answers and so on, and all the LEP data get archived in a fireproof vault at Fermilab, or wherever it is, and then somebody learns something new. Oh, that looks like there's a possible resonance in the B channel or whatever, and then people ask, well, if it is there, it should appear in the LEP data. And then you go ask the LEP data people for it, and they're like, hell no. Those data are archived, we're done. One of the reasons I'm very, very strongly in favor of open data is because data analysis is subjective. And as our beliefs about the world change, the kinds of data analyses we'll do are different. So for instance, right now, when I was your age, WIMPs were the dark matter candidate of choice. There's the WIMP miracle. It was also beautiful. All of our thinking about large scale and structure and everything was focused on the WIMP hypothesis, more or less. Then, of course, things evolved. Lots of new dark matter candidates appeared. Lots of great particle physics. And that made us reconsider some of our analyses. If those data had been closed and put away, there's no way we could have reconsidered those under new dark matter theories. So this subjectivity, so even though it's absolutely true, as you said, that there are things that the whole community agrees on here, it's notable things that the whole community agrees on evolve and change. And if we found some evidence that the LHC was producing missing transverse energy or something, I mean, we'd want to reanalyze all data sets in that context. Okay, good. So subjectivity has two aspects to it. People tend to think about the subjectivity like, oh, these people don't agree with those people, but that's actually not such as important as you won't agree with former you. 30 years from now, I hope you think completely different things about particle physics than you think now. Because if you think the same things in 30 years, this field is dead. And one of the things that's great about being in astrophysics is that sure as hell isn't true. I mean, planets were only discovered 10 years ago, and now planets are one of the main things we're working on. The expansion history of the universe was shown to be far more complex than we thought. We have lots of new channels for looking at dark matter that we've never had before. Things are changing and our beliefs are changing fast. And so though the subjectivity means that former data analyses will decay in value. And I will try to come back to that later in the week because it's so important. There's a lot of things where we as in the astronomy community have made mistakes where we produce, some catalog of objects, astronomical catalog of objects, and then we learn something new about the class of objects, and then the way the catalog was constructed ends up being useless now. It has to be reinterpreted, but we need to go back to the original data to reinterpret it, etc. So there's a lot of things where as your knowledge changes, your data analysis will decay in value. Good. Next. There's a lot of excitement right now about complex methods like deep learning. And you'd have to live under a rock if you haven't seen horses turned into zebras, or random photos captioned by machines. And people are very excited about these methods. These methods are very, very high performing methods that are used all over. But you'll notice that the biggest impacts of deep learning have all been in the commercial sector. They've been in targeting ads, making predictions for consumers, filtering content, identifying anomalies, almost all in the commercial sector. There have been very few really strong uses or successes of things like deep learning in the physical sciences. I'm not saying there have been none. In fact, I'm involved in working on some things. I'm not saying this is out. I'm just saying that it's dangerous as you go to very complex methods. Methods like deep learning are not theoretically understood right now by anyone, which means they're certainly not theoretically understood by the people in this room. And when we use them, it can obscure what we have assumed. Remember I said methods flow from assumptions. Like what are your assumptions when you turn on a generative adversarial network 17 layers deep with 1,500 nodes per layer and certain kinds of convolutional structure at the bottom end? Like what have you assumed? I have no idea, and nobody really does. There's some theory groups trying to do theory on deep learning, but it is not mature and we don't really know what's going on. So I'm not saying you can't use these things, but I think most of our applications are not applications for those things. And one of the options for later in the week, when we crowdsource the final lectures, would be a criticism of machine learning methods, because I've thought a lot about that. My group works close to the edge of machine learning, and we've been doing a lot of work on asking when do problems switch over from being machine learning is a good idea to a bad idea. And I've been thinking about that a lot. But, yeah, yes, hit me. Yes, yeah.
Where do you see the fundamental difference between using the neural network with the TFBA? Taking out of the analysis and what you know. Where does it change
I'm not particularly complaining about deep learning against any other exceedingly flexible models. So if you have any other unbelievably flexible model here, like a Gaussian process with a short coherence correlation length, or infinite order or high order polynomials or whatever, anything that's very, very flexible. That's where you start to lose control of what your assumptions are.
For example, the Higgs mass measurement that you're mentioning
Yeah.
is full of neural nets, right?
I know, but good. Yeah, so in the Higgs analysis, my understanding, and I am outside this field, so I don't know for sure, but in my understanding in the Higgs analysis, the deep learning methods are kind of used in a commercial way, in the sense that they are trying to build effective models of certain kinds of uninteresting aspects of the data. And in fact, I think that is the best use for these, to use them to model the parts of the data you don't care about. But even there are some dangers because, for instance, no one ever takes these deep learning models and samples from the prior, for instance. Because if you did, you'd find no sample you ever took from that prior is a function that you would consider to be reasonable in this context. So these function spaces, you can think of deep learning as being an immense function space. And these function spaces contain all sorts of functions that we would never abide as physicists. So I still think there might be some issues with the Higgs analysis from that. And of course, people are thinking about that a lot. You ask a great question. It's a detailed question. My view is that when you draw random functions from your function generator, most of them are a form you would never abide. You're using the wrong function generator. And then we can see what flows from that view. Good. One thing I always say here is if you need very flexible models for your work, if you're using them to model backgrounds or whatever, collaborate. You won't realistically be able to get a PhD in physics and fully understand deep learning in the 5-year period or whatever you've got, 3 years, 5 years, I don't know what length people are working on. So you basically have to collaborate. By the way, many of the methods in deep learning and machine learning come from physicists. And they're people with physics backgrounds. Because the branches of applied math that led to machine learning are the branches of applied math that were elucidated by physicists. So there's a lot of physicists in machine learning, and a lot of people who work in machine learning would like to come back and do something in physics. So for instance, the Facebook machine learning group, a big chunk of it sits in New York City, and I eat lunch there every so often because the food's amazing. But also the group there is very physics-y. There's a lot of physicists in that group. You can talk fully in physics language there, and I think a lot of them would be interested in getting involved in physics problems because many of them kind of moved into machine learning with some regret and many of them, the methods were really directly inspired by physics. For instance, I don't know if you've heard of the kernel trick, the kernel trick is a critical part of many machine learning methods. It comes up in Gaussian processes and support vector machines. That kernel trick is about making use of reproducing Hilbert spaces to generalize dot products. So it connects Hilbert spaces with linear algebra, and it's a beautiful thing that was done by a set of physicists or people with physics backgrounds. Good. That might be one of the reasons we haven't had much trouble when we've gone across the street and talked to people of finding people who want to collaborate, because really people do actually love physics. Despite it all, physics is still very popular. Good. Pragmatism. When we decide in my group whether we're going to do some data analysis using a frequentist approach or a Bayesian approach, we do not make those decisions on the basis of statistical philosophy. We make those decisions based on pragmatic considerations about what kinds of information we can bring in easily, what kinds of technologies we have available, whether we need probabilistic outputs or answers, what kinds of decisions we're going to make on those bases, whether we need to run many decisions per second, or whether we're just doing one in somebody's entire PhD. There's all sorts of different things that come up in different data analysis which push you towards being a frequentist or a Bayesian. So I'm partly talking about frequentism versus Bayesianism. And I work in both areas, and I think essentially all statisticians or data analysts who've worked for long enough have worked in both modes. You basically can't stay in one mode. Well, I mean, the particle physics community stayed in the frequentism mode for a long time. But even now, there's now Bayesian alternatives to most of the inferences that are being done in particle physics. And some of these, the differences between these will not be that one is magically right and one is magically wrong. They will have different properties, and they will be differently useful in different contexts. And I hope I can bring up some examples of that as we go. I will very much talk like a Bayesian a lot of the time. In fact, I already have talked like a Bayesian. Because, for instance, I've focused on subjectivity and utility. Those are things that Bayesians always bring up. But they, in fact, apply to all data analyses, frequentist or Bayesian. They're all contain subjective decisions, and they all involve utility at the end of the day. But they are places where the Bayesians are particularly sensitive. So you could have guessed I'm a Bayesian just from the way I'm writing down these rules. But I'm only a Bayesian in the sense that I do problems where the Bayesian approach is a much better approach. I also write some pipelines that have to move really fast, and then we do frequentism. So for instance, when we did a search for planets around other stars, where we ended up testing trillions of hypotheses, literally trillions of hypotheses. We sent all these all sorts of data and processes out into a big data center, and each of them did billions of hypothesis tests. You can't do a full Bayesian decision theory a trillion times, even if you're Facebook. So we fully formulated the problem in a frequentist formulation, and we were able to get the answers. Good. Next, and related. If you know things about your problem, you should incorporate that knowledge into your data analysis if you possibly can. So for instance, in astronomy, there's been people using machine learning to understand astronomical images. And astronomical images, imagine you have a little patch of the sky and you've taken a photo of it with a camera. You can see that it doesn't really matter what orientation I had my camera. In fact, we now have very, very strong evidence that the universe is isotropic and homogeneous. So it really doesn't matter what orientation I put my camera. It's like fundamentally doesn't matter. It's literally like a killing vector of the subject of astronomy, what orientation my camera was. And yet, when people apply these methods, it's hard to build in rotational symmetry, so they usually don't. And they just duplicate the data lots of times. And you see what's wrong with that? It means that the methods that are being used are spending a lot of their capacity to learn that things are circularly symmetric, not circularly symmetric, rotation independent. So you put in, the machine has to spend a lot of time and a lot of bits, and a lot of the information in your data just flows into learning that orientation doesn't matter, that this object's the same as that object. And that is blowing data. You're just destroying a lot of your data, and you don't even know how much you're losing for that, but you're definitely losing something, and you don't know how much. In fact, it's very hard to compute how much you're losing from doing that. So if you can incorporate that symmetry directly, your data analysis will work better. And this just cuts across all things, and of course, beautiful examples. The LIGO, extremely beautiful, I'll get you in just a sec. A beautiful example is the LIGO events. The LIGO events were found by template matching pre-computed black hole in spirals to the strain data from the LIGO events, plus coincidence. All of that is building in an immense, in fact, it's building basically all of general relativity into the detections, so that all the detections they've made are consistent with general relativity. The thing didn't have to search and find out that it looks like a chirpy in spiral. That was part. Now, of course, a flip side of that is they're less sensitive to events that don't look like chirpy in spirals, which means maybe there's some cool stuff in there. But when what your goal is to find the black hole mergers, or the neutron star mergers, you want to use every bit of knowledge you've got. It will just make you more sensitive, more accurate, and more precise. Yes, question?
Yeah, so, sorry, why if I have a learner and I show a picture,
Yeah.
and I rotate it a degree and show the picture again, and I just keep doing it, why am I losing?
You're losing, the question is, why if I just duplicate my data with different orientations and then train my machine learning, why am I losing? The reason you're losing is you've given the, one way to think about it is to think about it if you had very few images. Imagine you only had like 3 galaxy images and then you duplicated them many times. The model has something that's kind of ill-defined, which is like its capacity. It has capacity to learn a lot of different things, because this is a kind of model that can find kittens in YouTube videos or whatever. And it's got to reduce that capacity by seeing what are the commonalities in the data. And to see that these images were all the same somehow, it's sort of using the information in those images to learn this commonality rather than to learn something about galaxies. It has something to do with that. It has to do with the fact that the capacity of the model can learn things that aren't rotationally symmetric, so it has to discover in this duplicated data that things are, in fact, not. And then, of course, if you go further, then it'll figure out that actually you only did it k times, and then it will learn that the data sets have k copies of things in it, and then it will think that that's a feature of the data set, that there's k copies of everything, which, of course, you didn't intend. Good. Shall we? I have lots more to say about this. This gets back to the original thing about methods flowing from assumptions. Because what are our assumptions? You know, when you're finding out the Higgs mass, your assumptions are the standard model plus some parameters, and then some things about the instrument and backgrounds and colorimeters and whatever, bunching, overlap, whatever all that stuff is. As you can imagine, it is not possible to put all of your knowledge into every data analysis. Not everything that's known about the LHC was incorporated in the LHC data analysis. It's just impossible. Like if you try to put everything in, you'll generally get an intractable inference. So there are things that are known about the detectors in the system in the LHC that were not used in the data analysis. And there are things that were used in the data analysis that are only approximately true, because the data analysis had to also get done in a finite amount of time. See how these things are all thread together, right? You could have done a better data analysis, but it would have taken much more time, and then that would start to conflict with certain utility things like not getting the project canceled. So you can't, I'm saying that knowledge rules. I'm not saying you must always put all of your knowledge in. You will not be able to afford to put all your knowledge in. And sometimes your knowledge is very qualitative. Sometimes your knowledge is like, that doesn't look right. And it's hard to put, that doesn't look right into your data analysis. But when you can, it will help you. Yes?
Going back to point 2 about the subjectivity, isn't it generally a good idea to put in as few pre-assumptions as possible when you're processing your data to avoid that kind of bias?
Good. Great question. The question is, coming back to point 2, shouldn't you put in very few of your beliefs, because the whole point of the data analysis is to learn these things? That's a great question, and it depends a lot on what your goals are. If your goal is to measure the mass of the standard model Higgs, then you should put in everything you know about the standard model and its possible Higgs, because your goal is to measure that mass. But often your goal is very different. You might be looking for missing transverse momentum. And then you might want to make a much more general model that depends as little as possible on the details of the standard model and depends only on what you know about kind of kinematic properties of the data set, so that you can do reconstructed transverse momentum and figure out whether some of it's missing. So I think a lot of the question of like where you draw the line of what you put in and what you don't put in depends on what your goals are. Once again, we're back to subjectivity. Some people look at the LHC data and they ask, what's the mass of the Higgs? Those people are going to put in all of their standard model assumptions. Other people are going to look at the Higgs data and say, oh my God, there might be a dark matter candidate in there. And then they're going to put in much weaker assumptions because they want to be available. They want to be able to find things that haven't been found. So for another good example that's very related to what you asked is LIGO. If LIGO wants to measure the black hole merger rate under the assumption that general relativity is substantially true, then the right thing for LIGO to do is to put in the best computations of black hole mergers they can possibly make and do template matching to find the events. But if what they want to do is ask whether general relativity breaks down within one Schwarzschild radius of a black hole, then you want to weaken that substantially and ask, are there events in the data that we can see that are reliably there but don't look like general relativity? So again, that's a very nice point, actually. You brought up a point, which is that I've been too weak here. It's not just that all data analysis is technically subjective, but even the goals of data analysis are subjective. And so what you choose to put in or leave out depends on your goals. And by the way, since I am in astronomy, I do a lot of detailed Bayesian analyses where we are trying to measure, make a very hard measurement. We're trying to measure something that's very obscure in the data and very hard to measure. One of the criticisms we often get is, look, you've put everything in your data analysis. You're only going to get out what you expect. And there is an element of truth to that in the sense that you want to do something different for measurement or discovery. Measurement is different from discovery. That could have been one of my points. That could be point 9. Measurement is different from discovery. But I wanted to re-emphasize in the answer to this that all the assumptions we make are testable. So, though the LIGO group used general relativity templates to do its discovery, make its discoveries, it can then take the data and ask, are the data consistent with general relativity? And it's not in conflict to do that. It's true that if something looked very different from general relativity, they wouldn't have detected it. But if something looks very similar to general relativity up till the last microsecond, they could see that. And so their assumptions about general relativity are testable. I had 8 things to write on the board, and I've written 8 things on the board. I wanted to make a few comments about what I'm going to do next. Would people object if I go 2 more minutes longer? Okay, my plan for the next few lectures is the next lecture I want to walk through an unbelievably trivial data analysis. So like you'll be able to just like enjoy it. We should bring beer. Just to walk through what does it look like to write down the assumptions and how does the method flow from it and what changes if we don't do it. It's really trivial. It's really like undergrad lab level. So that's first thing. Then I want to do something on MCMC because I'm a big fan of MCMC and a lot of people will end up using MCMC in their research. So I'll talk about, that's Markov chain Monte Carlo. Then I'm wide open for the last 2. I have ideas about model selection and decision making. I have ideas about machine learning. I also have a like, what are the most important ideas in machine learning kind of lesson or whatever that I could give. There's various things I could do. So I don't know what people were talking about crowdsourcing things a minute ago, or well, an hour ago now. I don't know if the wiki is the best place to do that. Does everyone here have edit rights on the wiki? Is there a mechanism for crowdsourcing things? Facebook. Who's on Facebook? I would have believed it if you said there's a Snapchat channel for an Instagram. No, I'm kidding. I'm not on Facebook, unfortunately. We could open up a Google Doc or a Google form. But anyway, I will think of some forum where people can weigh in and we could just brainstorm, like throw in questions and stuff. And then I can build some last 2 lectures out of questions. But when we reconvene for me in the afternoon, we're going to talk about a very, very simple data analysis, which will be just embarrassingly simple. So have a beer at lunch. I'm done.